Okay, here we are, quiz 10. Almost everyone in the class would benefit from watching this, especially if you got less than an 8. But even if you got a 9, it might be beneficial for you to watch this. So you see in front of you, whoops, the 2 questions of the quiz, and over on the side I've put the equations from rotational kinematics. So read through this if you forgot. And A is how many radians are there in 4 rotations. But before you do that, read the information and draw a diagram. I think it would be helpful. Some of the mistakes that you made might have been avoided if you drew a diagram. So do a diagram and then answer A. So pause this video, draw a diagram, and then answer question A. Okay, I haven't done part A yet. Here's the diagram. I think it's worth going over the diagram. Now notice I did spend 5 minutes drawing this diagram, but the quiz you have 35 minutes to an hour to do it. So the 5 minutes here will be well spent because a lot of you made mistakes by choosing the wrong numbers. So notice, check your diagram and see if you've got everything in here. So the basic, I forgot the time. Anyway, I put in the total number of rotations. We're going to convert that to radians in part A. I should have listed that the time is 5 seconds, the total time. But, so I put the mass, the 2 masses, and the delta y. We don't use this. Actually, these numbers are slightly different from what you had in the quiz, but we're not going to use these anyway. The important thing is that the width of the flag is 2.5 centimeters, and you're going to need to use that. And that the flag is 10 centimeters away from the axis. That's the radius of the disk, because the diameter is 20 centimeters. So I put the radius of the disk. And I showed the diameter of the hub. That's also important. That's 4 centimeters, but the radius of the hub is 2 centimeters. So this value for the radius of the hub, and this value for the radius of the disk, and this value for the width of the flag, a lot of those numbers you confused using the diameter or the wrong number. So this is why I think the diagram, time spent doing the diagram, gives you a chance to think through the details of what's happening in the problem and make it less likely that you'll make mistakes once we start calculating. Okay, so now I'm going to pause. Now you can pause if you haven't done A and do A, or just keep watching. Okay, most of you got this right, but not all of you got the formatting right. So when we do units conversion, remember we write the number down and then we write the conversion factor as a fraction with the units, and we cancel the units that we're trying to eliminate. And so 4 rotations multiplied by the conversion factor, 2 pi radians over 1 rotation. This is like multiplying by 1 because these are equal, but the rotations cancel and we end up with units of radians. And you can leave it 8 pi, but for calculation purposes it's better to do this. And notice I kept extra digits. So when I report this answer, and I should have done another equal sign and written to 25.1 radians, and that would be my final answer with 3 significant figures. So a lot of you are forgetting to pay attention to significant figures. Okay, do part B and come back. Okay, so most of you got this one also, but notice you didn't all have the formatting right. So notice I take an equation from the equation sheet for omega average. I write down the unrounded number from the previous problem. I still have that on my calculator, so I just divide it by the total time, the 5 seconds, and I get 5.026548, blah, blah, blah. I recorded the 5.027, so this is the number I'll use for calculation. But the answer I'm going to report, is the 5.03 because that's 3 significant figures. And notice I have units with the numbers and units with the final answer. So remember the units, remember the significant figures. All right, do C. Actually, you might pause and do C and D together because there's two ways of doing these two. So go on and do D and then come back. Okay, so the direct way to get omega final from omega average, which we just got, is to double it. But you won't find that equation on here directly, right? But if you go down to equation 2 and you divide both sides by t, you'll see that delta theta over t is omega average. So, or you might just remember that when the acceleration's constant, omega average is the average of the final and the initial velocity, and write this equation down. If you wrote this down, it's better than not writing any equation, but you'd be better off to start with this. Omega final then is twice the average, and you get 10.01, but it's actually 10.053 radians, so I'm going to save that. Now, if I have omega final, the easiest way to get the acceleration is just to use this average acceleration equation, which is this equation here. So you could start with this one, or if you were just looking at these equations, if you rewrite this, you'll get the same thing. You'll get that alpha is the change in omega final minus omega initial over t. And when I do that, notice I wrote the numbers. I didn't write the rounded number. I wrote the units, and I have my answer. And this number, I should probably record it, is 2.0106. So it's pretty close to 2.01. That's why I didn't include those other digits. But strictly speaking, I might have, I'm saving the 06 on my calculator. Now, what's the other approach to doing C and D? The other approach, if you want to try it, is to do D first and then go back and get C. So if you want to try that, okay, or if not, just watch what I do. So here's the other approach. We have used this equation a lot, right, for getting accelerations, whether they're linear or rotational. So we start with equation 3. And since we start from rest, this is 0. We do the algebra, we get this equation. Notice I use the 25.133, the unrounded number of radians, and divided by t squared. And I get this value, the same value we got in the last set. And then I can bring this up here and use equation 1 of the kinematics equations to find omega final. I didn't write it out, but it gives me back the exact same value to 5 significant figures that I got back here doing it this way. So this is actually, in some ways, an easier way to do it. You don't have to always do the problems in the order that they're given. Okay, so now proceed and do E and F. So since we have omega final, where is it? There it is. We can get the tangential velocity at the end just by multiplying omega times r. That's this equation here. And so the omega final, the omega at the end, is the 10.053. Notice I use the whole thing. Notice I put the units in times the radius of the disk, because it's the distance the flag is from the center of the circle. And so I put that in meters, 0.10 meters, and that's the radius, so it's meters per radian, and the radians will cancel. And so we end up with 1.01 meters per second. And since we know the final tangential velocity, we can use this equation, right? Velocity equals the distance over the time to get the time. So velocity, the tangential velocity, that's how, if we were measuring it with the photo gate, right, we'd take the flag width divided by the time to get the velocity. Here we're going to use it to get the time. So the delta x is the width of the flag in meters. The velocity at which the tangential velocity at which the flag goes through is the 1.00 meters per second. If I cancel the meters, which I didn't do, you end up with about 0.025 seconds or 0.0249 seconds, depending on the number of digits you keep. There is another way. If you wanted to get if you wanted to use omega final to get the value, I can show you how to do that. So notice this other way of doing it. Some of you did it this way. Since we know omega final is going to be the angle of the flag going through the gate divided by the photo gate time, right? That small angle that's formed by the flag at the end of the disk is the angular displacement as the flag goes through the gate. And so to get the photo gate time, we just take that small angular displacement and divide it by omega final. And the small angular displacement, for any angle theta, it's the arc length over the radius. So 2.5 centimeters is the width of the flag. 10 centimeters is the radius of the disk, and so that gives you 0.25 radians. And if we put that here and divide by the omega final, or is it the 10.1 radians, you'll get the same answer that we got earlier, the 0.025 seconds. Okay, last step is to answer for these three accelerations. So this is an important question, and it's teaching you how to explain physics concepts in words, equations, diagrams, and examples. And the equations are essential. So make sure you have an equation for each one. And so we have three different accelerations: tangential, centripetal, and angular, or rotational acceleration. So we're talking about acceleration, not velocity. So here's how, ideally, you might have answered those questions. But before I answer, just think about each one of them. Think about what the symbol for each one is. Find the relevant equations over here, and then we'll write the equations, and we'll write the explanation in words, and we'll give an example. So pause and come back. So notice I rearranged them for convenience of explanation. The easiest one to explain, I think, is the angular acceleration. And the angular acceleration, acceleration in general, is change in velocity over change in time. So angular or rotational acceleration is the change in the rotational velocity. It's the rate at which the rotational velocity is changing, and it could be increasing or decreasing relative to time. So this is the definition, and those are the words that go with the definition. And an example would be the turntable. When the mass falls, the rate at which the disk is spinning spins faster and faster. And so this would be a measure or a calculation of the angular velocity. The centripetal and tangential velocity are linear velocities and need to refer to an object. So notice the flag and the disk have the same angular acceleration. Their angular velocity changes at the same rate. But the speed, the rate at which the tangential velocity of the flag increases, is going to be different actually from how the mass falls, right? Because this is further away from the axis. The string is wrapped around the hub. So as the angular velocity changes, so does the tangential velocity. And so we can go to the conversion equations and we could say that, oh, tangential velocity equals the tangential acceleration equals the angular acceleration times r. But that doesn't really tell us what it is. It tells us how to get it from the angular acceleration. What it is it's the rate at which the tangential velocity is changing. So if we took the initial tangential velocity of 0 and subtracted it from the final tangential velocity and divided it by the 5 seconds, right, we would get the tangential acceleration. So when you're explaining what it is, it's the rate at which the tangential velocity is changing. But in the case of centripetal acceleration, even if the wheel were spinning at a constant speed, an object on the wheel or the flag would have a centripetal acceleration. And you can calculate that, as we did earlier, either by taking the velocity of the flag squared divided by the radius, or if we use the conversion equation, right, Vt, V tangential equals omega r, so if we take omega r and square it, we end up with another equation we can use for calculating. Now, how do we understand the centripetal acceleration? The centripetal acceleration is the rate at which the velocity vector is changing. And in a case where the wheel is spinning at a constant rate, there's still a centripetal acceleration because the direction of the velocity vector is changing. So it's the acceleration toward the center rather than the acceleration of the object tangent to the circle. So they're in two different directions. Distinguishing these two is a little bit tricky, but at a minimum you have the equations, then words to explain the symbols in the equations, and then if you can relate that to an example like the flag has an angular acceleration, it has a tangential or linear acceleration, and it also has a centripetal acceleration because its direction is constantly being changed and kept toward the center of the disk. So remember, next essay question, start with equations, use words to explain the equations and the concepts, and then try and relate it to an example from the lab.